Okay, so in the previous part, we proved this second formula. Let's see how we can obtain the other three. Again, from now on, you're going to use these formulas directly, but just in the name of practicing more with these operations, I'm going to show you how to obtain these three ones. And because again, the whole idea is to practice with these as much as possible and then essentially use them as you just use any other formulas involving derivatives or integrals of regular functions. So these two formulas are obtained by plugging in, by bringing into the summation these x to the n or x to the minus n and differentiating inside the summation. But you could also rewrite this whole thing in terms of the product rule. And if you do that, you're going to eventually obtain the third and the fourth formula. So on one hand, the left side, you can apply the product rule from calculus 1, right? So minus n x to the n minus 1 jn of x, and then plus x to the minus n jn prime of x. And again, if you differentiate inside the summation, one can show, on the other hand, this is minus x to the minus 1 jn plus 1 of x. Same thing here. If we apply the product rule, we get n x to the n minus 1. Oh, this is minus 1, excuse me. So on the first one is minus n x to the minus n minus 1. So on the second one, it's n x to the n minus 1 jn of x plus x to the n jn prime of x. And on the other hand, we showed it's x to the n jn minus 1 of x. So now it's just a matter to obtain the third and the fourth formula. It's just a matter of multiplying these equalities by the appropriate power of n so that you're left with just x jn prime. Okay, because these are formulas for x jn prime. So to achieve that, notice I need to multiply the first row by x to the n plus 1. Again, x to the n will eliminate x to the minus n, and there's another x to be left there together with jn prime. By the same token, the second row needs to be multiplied by x to the minus n plus 1. X to the minus n again eliminates x to the n, and then you're left with an extra x together with jn prime. So when we multiply all the way through and simplify, then the first row becomes minus n jn of x plus x jn prime of x equals, let's see, if I multiply by x to the n plus 1, you're left with x. And on this one, if I multiply by minus n to the x to the minus n plus 1, you're left with n jn of x plus x jn prime of x equals x jn minus 1 of x. So notice that if I get x jn prime by itself in both of these equalities, you end up with the third and the fourth formula. So x jn prime of x equals n jn of x minus x jn plus 1 of x, and there it is. And then the last one, x jn prime of x equals minus n jn of x plus x jn minus 1 of x. And that's the fourth formula over here. And finally, the last one, which is a very useful reduction formula, a recurrence formula that allows you to go from a higher order down to order 1 or 0. So you can repeatedly use this formula to write any Bessel function of any order n, a natural number n, in terms of, if you keep on using it, you end up with 1 and 0 here. So a recurrence formula that brings everything down in terms of J1 and J0. And this last formula is simply setting this equal to each other, right? So these two are the same, xj and prime. So if you set them equal to each other, you get n jn of x minus x jn plus 1 of x equals minus n jn of x plus x jn minus 1. And if we get this by itself, if you move it to the other side, and this to the left side, njn plus another njn makes it 2n jn of x, and then minus x jn minus 1 of x. So this is how you get the last formula. Again, if you still wonder why we bother with these formulas, is because essentially you want to write down pretty much anything you know or anything you can obtain in terms of recurrence formulas, so something that brings the order down, and in terms of different derivative rules. Because later on we have to integrate or differentiate Bessel functions, and you can think of these as one of the most basic differentiation or equivalently anti-differentiation rules. As a rule of thumb, so let's write it as a remark here, you need to basically get the final answer pretty much in most of the problems you're going to end up with in this class. So get the final answer in terms of j1 of x, j1 of x. So these formulas pretty much in most of the cases allows you to do just that. And speaking of j naught, remember that the Bessel equation of order 0 is the one that will appear most often. If you go back to the beginning of the chapter when we introduced the concept of Bessel equations, you would notice that the Bessel equation of order 0 when n is equal to 0 is the one that pops up as the Sturm-Liouville problem. So it will be very useful actually to write down on your formula sheet some of these formulas when n is equal to 0 or n equals 1. So in other words, write down what these formulas will tell you if you plug in the lowest value possible for 0, in particular for the first two ones. So for instance, in the first case, in the first formula here, if n is equal to 0, that gives you basically x to the 0, which is 1. So that gives you a formula for the derivative of j naught, which simply states that j naught prime is minus j1 of x. All right, so that's simply replacing n equals 0. If I replace n with 1 in the second formula, that will give you x times j1 of x prime, so the derivative of the product equals x to the first, which is just x j naught of x. So keep this in mind because these will appear often, as I mentioned before. You can think of this as a rule for differentiation of j naught and for xj1. Or equivalently, you could think of this as giving you an antiderivative for j1 and an antiderivative for x j naught of x. Just make sure you bring the minus over if you do the integral instead of the derivative, just like you do for any known differentiation rules. It's equivalent to a rule for taking the antiderivative. And make sure you don't confuse this. So notice that there is no antiderivative. I mean, there is no closed form for an antiderivative of j naught of x. That's why you'll see later, if the problem ends up being, the answer to the problem ends up being an integral of just j naught, you leave it in that form usually because there is no closed formula for the integral of j naught. If you end up with x times j naught in the integral, then of course you can integrate it immediately because you can replace this with, you can replace this in a differentiation form. So in other words, you know the antiderivative of xj naught is xj1. So make sure you don't misuse the formulas. That's my point here. You have to, in the beginning, practice with these formulas carefully and make sure you don't misuse them. So let's move on the third part with the formula for the integral, or reduction formula for an integral. and then you'll see how these formulas can be used repeatedly in the same problem. So stay tuned for the third part.